Let's take a look at some common misuses of statistics. Suspicious samples. Suspicious samples can fall under multiple categories. Do we have a small sample? Because small samples can generate all kinds of results. How did we gather that sample? In a previous video, we talked about probability sampling versus non-probability sampling. Non-probability sampling does not give us a fair representation of the population. So if a non-probability sampling technique was used to gather the data, we cannot generalize any conclusions to the population. Breaking down small samples a little bit further, we should not conclude something based on a sample that is too small. Percentages are very deceptive because they hide the true numbers behind them. But percentages are important because they help us compare two sets of numbers that could be wildly different in size. We'll see that a little bit later. Another misuse of statistics is something called ambiguous averages. We haven't talked about averages yet. That'll come in the next chapter. When the word average is used, it could mean one of 4 different calculations: the mean, the median, the mode, or the mid-range. All 4 of these are considered averages. So if someone is trying to make a claim, they can use one of the calculations that best supports his position. In the picture, we have 5 children whose heights are listed in centimeters. You can see that the mean, the median, and the mode are all different numbers. And with them being different, if we had something to say about this group of children, we could use the number that best supports what we want to say. Changing the subject or using relative numbers instead of actual numbers. So here, 3% versus $6 million. 3% sounds really small. 6 million, depending on the context, could be really big. For most of us, $6 million is really big. And shown here is a comic by XKCD. XKCD is a comic strip online, usually purveying math, science, things in the STEM field. But this is a good example of conflating percentages with actual numbers. Another example of changing the subject, but in a different way. Here we have a graph that is intended to compare the number of people on welfare with the number of people with a full-time job. The source is from the Census Bureau in 2011, but what hides behind these numbers is how they counted the data. For people with a full-time job, they counted actual individuals who have a full-time job. But for people on welfare, they didn't just count the one person that receives welfare, they counted a whole family. So what I mean by that is, if you lived in a household with your other family members, and let's say your uncle came to live with you for a short amount of time, and in that year, your uncle received some form of welfare. This 108.6 million doesn't just count your uncle. It also counts everyone else in your household. So it's very deceptive in how they are counted. We're counting individuals with a full-time job, but we're counting whole households of people in the welfare number. Another example of misuses of statistics are detached statistics. In detached statistics, no comparison is made with a statement. 1/3 fewer calories. This granola bar has 1/3 fewer calories. Fewer calories compared to what? Or, our medicine works 4 times faster. 4 times faster than what? There's never a comparison. The closest image I could find to something like this, given here on the right, the Fruit Loops box, you can see in giant yellow letters 1/3 less sugar, but at least they're doing a little better on print material. They have the comparison in smaller letters underneath. But still, be very wary of comparisons made when they don't tell you what they're comparing it to. One of my favorites, and probably the most used misuse of statistics, at least in everyday life, are misleading graphs. We want to carefully regard the shape of the graph, how it's drawn, where the data is coming from. We want to consider it with a critical eye. Most graphs aren't necessarily bad, but if they're created with an intent to deceive, there's a problem. So some questions to ask yourself when you're looking at a graph. Are the axes drawn to scale, or is one cut off? You'll see some examples here in a minute. Is the graph using shapes instead of bars or lines? Do we have a pictograph instead of a bar graph, a line graph, or a pie chart? Are labels and units given so that we are fully able to compare and understand what's going on in the graph? Are we comparing two or more sets of data? Do we have two vertical axes instead of just one? Is there a source provided so that we know where they got the data from? We'll take a look at some of these examples. Before we do, a mild disclaimer. Anything shown in this video isn't intended to support or refute any particular political party or agenda, but merely used to show how statistics can be misused, how statistics can be used to deceive. And unfortunately, politics and advertising are two of the main uses of misleading statistics. We've already seen one graph. Going back to that graph really fast, notice from those 5 questions, we don't have anything on the vertical axis. The one over here on the left, we have no numbers. And then my next thing to point out, notice that 101.7 million, that bar looks really short. I'm only adding almost 7 million to get to the people on welfare. This is 101 million. This very much larger bar is only 7 million more, but it looks at least 4 times as big as the other one. An instinctual reaction in your brain is that, wow, there are a lot more people on welfare compared to those with a full-time job, just by the way that the graph is drawn. Here's an example of a bad use of statistics, even though the graphic is pretty visually interesting. Here we have a pictograph released to show the high school graduation rate while President Obama was in office. And you can see from right after President Obama was in office, we have 75% high school graduation rate. And then close to the end of his tenure, it has increased to 82%. This is great. We have more high school students graduating. Do you see the deception? At first glance, the picture makes the change look drastic, when in fact, from 75% to 82%, it isn't that large of a change. Notice the 75%, we have 5 books stacked, but in 82%, we have 17 books. It's over 3 times as tall, but 82% is not 3 times larger than 75%. Hence the deception. They released a similar picture, again showing that increase. Again, great work. High school students are graduating. In this graph, you get a better sense of a possible misuse with this y-axis, the vertical axis over here. We don't start at 0, we start at 70%. So we're cutting off the bottoms of these bars by starting at 70%. And so the comparison between the first 2 years and the 5th year looks more dramatic than it is. If we make the correction and change the graph so that we start at 0, we can still see that steady increase, but it does not look as dramatic as the previous pictures. Again, it's great news that our high school graduation rate is increasing, but the pictures can be misleading. Another example of misleading graphs tend to center around images used instead of bars. So in this picture, used by Yale University to help teach the teachers how to teach statistics, you can see that in 1960, we have a small trash can indicating 100, maybe pounds. There aren't any units listed, so we're not sure. We have to guess. So 100 pounds of trash, maybe. 1980, it's about 200. And in 2000, it's 250. But the deception comes in your instant view of the graph. The first moments that your brain looks at the graph and tries to process the information. This is where the deception happens. Notice in 1960, that trash can is very small, both short and narrow. and we move to 2000, the height of the trash can corresponds to the amount, but instead of keeping the trash can the same width to make a uniform comparison, the trash can has been increased. The trash can in 2000 has its width increased as well. So your eye is drawn to the volume change of the trash can, not just the height change, making the last trash can look more than 4 times bigger than the first trash can, when the absolute change between the two numbers is really only 2.5 times. Another example of a misuse of statistical graphs. We're shown some data about Planned Parenthood. This graph was shown in 2015 when the United States Congress was questioning the president of Planned Parenthood about a misappropriation of federal funding. And Representative Jason Chaffetz of Utah explained the graph, saying the pink shows reduction in breast exams, the red is increase in abortions. His ultimate point being that your preventative services are decreasing, but your abortions are increasing. And this is not acceptable. That was his point. And at first glance, we see cancer screening was 2 million in 2006 and has decreased to 935,000 in 2013. And abortions have increased from 289,000 in 2006 to 327,000 in 2013. But why is 327,000 above 935,000 on the right? Why is this smaller number graphed above a larger number? That's strange to my mathematical mind. So there were some, we can correct it. We can take the data and create a more accurate graph. But the other point to make too is that there's no vertical axis. There's no measurement on the y-axis, the side, that would help us better visualize this change. So let's graph it. Let's change it. Using the data, we can change the graph so that it's more representative of what's actually happening. And we see abortion procedures in purple and the cancer screening and preventative services in blue. This graph definitely does show a decrease in the cancer screening, but looking at the abortion procedures, it seems to be pretty steady in comparison. Even this graph can be somewhat misleading because we're comparing a small amount, less than 500,000, to a much larger amount, 2 million. So now, instead of looking at absolute numbers, let's change it to percentages. Percentages allow us to compare numbers of different magnitudes. So percentages, even though previously seemed bad, are not always bad. They actually can be quite good. So in this graph, we're comparing the percent change from year to year. Abortion procedures in purple initially increased to 2009. Pretty much in 2013, there wasn't much of a change at all. This graph does show that the cancer screenings and preventative services have gone down. This graph gives us a better comparison of what's happening than that original picture that the representative tried to show to make his point. Another example of a misleading graph. Here's a comparison of the cost of a 4-year degree from 1964 up through 2010 versus salaries for people who have earned that 4-year degree. The point being made by the article is that tuition is skyrocketing while salaries are almost staying the same. And although tuition is increasing, what's not clear in this graph that you have to think about is that we're talking about one 4-year cumulative cost. So we're adding up the cost for 4 years, and we're comparing that 4-year cost to a single year's worth of salary. But we earn that salary until we decide to change our jobs. We're comparing two very different things, two very different scenarios, and it creates an unfair comparison between the two. Another one of my favorite misuses of statistical graphs. Here's a graph created for the 2012 presidential election. In 2012, we had a lot of Republicans in the field, and Opinions Dynamic ran a poll. The intent of the poll was to determine who were people backing. Who were people supporting in this presidential candidacy? And we see that 63% were supporting Governor Huckabee, 60% were supporting Governor Romney, and 70% were supporting Governor Palin. When we use pie charts, the intent of the pie chart is that all of the regions add up to one whole, or 100%. These add up to almost 200%. It's a pretty terrible graph to use to compare three percentages. If they truly wanted to compare these three percentages so that we would understand what's going on, they would have done it in a bar graph, as that would have been an easier way to compare the percentages. Here, these three regions pretty much look the same, and it's just a bad use of a pie chart. Another bad example of statistics. Here's some data on the employment rates under President Obama for the year 2011. Coming from the Bureau of Labor Statistics. I'll give you a second to see if you can see what's wrong with the graph. 8.8% sure is close to 8.5. But if we come all the way over here, 8.6% is actually above 9%, which is very weird. I think maybe they were throwing this graph together too quickly and maybe didn't double check the data. Correcting it, we get a graph that looks like this. Very much a different story compared to the previous graph. Another situation of misleading graphics in politics. Here's a graph indicating the number of murders committed using firearms in Florida. And they make it a point to show in 2005, Florida enacted its Stand Your Ground law, which gave people a legal right to match force with force if they were attacked. And it seems, at least from the graph, first glance, gun deaths have decreased. But if you really start to analyze the graph, you'll notice 0 is at the top, not at the bottom. This one is very misleading. Flip it around so that it's correct. Correct in the way that we think graphs are normally graphed. And we see that, sure enough, we had a decrease until 2005 and a pretty steep uptake immediately following. This graph does not support that the Stand Your Ground law increased gun deaths. Although it could be used to argue that, we cannot determine if the Stand Your Ground law caused more deaths. More on that in just a few seconds. Another example of a misuse of statistics is self-interest studies. Who is funding the study that these statements are coming from? In the example here, 2 8-ounce glasses of milk per day help maintain a healthy weight. But maybe what's hidden, dairy farmers and milk producers were the ones who funded the study. Another example in real life of a deliberate distortion and a self-interest study. Before 2007, Colgate was running this ad. More than 80% of dentists recommend Colgate, while the Advertising Standards Authority in the United Kingdom ordered them to take it down because of its misleading use of the statistics. It turned out that Colgate ran a study with dentists and asked them, which toothpastes would you recommend? The dentists weren't required to pick only one toothpaste. They were allowed to pick as many different kinds of toothpaste as they wanted. So many of the dentists picked multiple brands, Colgate being one of them that was more often chosen. But this statement, more than 80% of dentists recommend Colgate, is very misleading because it makes us think, the consumers, think that 4 out of 5 dentists are recommending Colgate, when in reality they aren't. They're recommending Colgate and some other brands. Remember when we were going to talk about correlation and causality? Correlation. Just because we have a relationship existing between two variables does not mean that one is causing the other. Humorous cartoon shown here, we have increase of ice cream being sold and an increase of shark attacks. So does that imply that ice cream causes more sharks to attack? No. We're looking at summer months where more ice cream is being sold and more people are going to the beach where the sharks are. And thus we have increases in both. If we're observing, if we're collecting data through observation, we cannot make a claim about causality. Correlation means there's a pattern. There's a relationship between the two variables that we're considering. But if two things are correlated, then we have one of 5 different possibilities. One could cause the other. The two could actually be caused by a third. There could be some kind of cyclical relationship, or it's just coincidence. So we have to be really careful about correlation and causality. Just because two things are related does not mean that one caused the other. Here's some pretty humorous examples found on the net. This graph shows in red the number of people who drowned by falling into a swimming pool, and in yellow the number of films that Nicolas Cage appeared in those years. And you notice the two graphs look very similar. In chapter 10, we're going to talk about this correlation number down here. The closer it is to 1, the better the two data sets are correlated. So 0.66 is pretty close to 1. They're pretty correlated. So no, Nicolas Cage shouldn't necessarily retire. He's not causing people to drown by falling into a swimming pool. But we have this odd relationship happening between the two variables. It's just coincidence. Here's another example of coincidence. We have fresh lemons imported to the United States from Mexico in metric tons along the x-axis down here. And we have the United States highway fatality rate along the y-axis. We have an almost perfect correlation between the two data sets. We know lemons are not reducing highway fatality rates. And another one, it was recently reported that Microsoft was finally going to end Internet Explorer. But back in the early 2000s, we see in green bars the Internet Explorer market share, so how many people are actually using Internet Explorer, and that's being compared to the number of murders in the United States in blue. And there seems to be a pretty strong relationship between the two variables. Again, coincidence. Another example of misuses of statistics are faulty survey questions. Merely the way we phrase the question can induce an answer that we want. Here are 2 examples. The first pair, one question, do you think that teachers should be paid higher salaries? The second question, notice the change. Are you in favor of increasing tuition so that colleges can pay teachers higher salaries? So trying to influence the way that they're being answered. The second pair, do you believe that the school district should build a new soccer stadium? Or do you want to increase local taxes so the school district can build a new soccer stadium? Eliciting a different response compared from the first to the second. More misuses of statistics that can occur. The way we order questions in a survey, not responding to a survey, refusals. Very precise numbers when we're talking about large amounts of things. So an example of a precise number, 5,423,721, when we're talking about something like the number of mice in a neighborhood. How do you count the number of mice if they're all running around and they're hiding? Partial pictures, we're obscuring something going on, and deliberate distortions. Similar to partial pictures, we're creating a distortion. We're hiding information. We're not telling the whole story. So when you're faced with statistics in the media, in politics, in the real world, look at them with a critical eye. Analyze them. Don't let your emotional first impression or first response, first view, overtake your rational brain. And try to dig deeper and see what's really going on. What are they trying to convey? What are they trying to persuade? Are they using the data, the graphs, the information responsibly and reasonably? Or are they using it to deceive?